Thank you all for being here. My name is Yihui. Today I'll be talking about quantum learning in the presence of noise, and not only noise, but also random circuits. And this is really an area that has only taken off in the past, I would say, decade. So I'm excited to be presenting these results to you today. So why do we care about noise? Well, it's part of NISQ. And you could even say that it is a defining characteristic of NISQ computation. As an example, Google's fidelity for their quantum advantage demonstration was just 0.002. So this tells you that noise is very much a part of these circuits. And I would even go so far as to say, kind of hand-wavingly, of course, that the question of whether we can compute with noisy devices reduces to the question of whether we can extract signal from noise, or is the level of noise too high that it's impossible to extract any signal. And today I'm going to give you some partial insights into the answer to this question. But it turns out that the answer is surprisingly sensitive to how you model the noise. And we're going to see kind of that noise is both good news and bad news. So I'm going to start off with a popular noise model called depolarizing noise. So how many of you kind of have some idea how depolarizing noise acts? Yeah, okay. Excellent. So just to maybe interpret the math, so what depolarizing noise does is that it replaces your quantum state with the maximally mixed state with some probability, and with the complementary probability, it does nothing to your state. And so how you would model depolarizing noise acting in your quantum circuit is that you assume that every gate is followed by one such noise channel. So what is depolarizing noise doing, actually? Well, I argued that depolarizing noise is, you can think of as an entropy increasing agent. So when you substitute in the maximally mixed state in the argument of the noise, so depolarizing noise is going to kind of preserve the maximally mixed state, maybe give it some kind of like amplitude at the front. But the point is that depolarizing noise is a kind of unital noise, which means that when it acts on a maximally mixed state, it preserves the maximally mixed state. And because the maximally mixed state you can think of as the quantum analog of the uniform distribution, so we can think of depolarizing noise as something that drives you towards the uniform distribution. So it's a noise that really loves chaos and entropy. However, that is not the only source of noise in hardware. And many of you know much more about hardware than I do, but these other sources of noise in hardware can actually decrease entropy. This means that when you act with the noise on your state, it actually does not drive you towards the maximally mixed state. Instead, it drives you towards some other state. So it's very interesting when in hardware you have both of these kinds of noise present. So if you model your noise in your hardware solely as depolarizing noise, that is usually bad news for your quantum algorithm. And here are two examples of aforementioned bad news. So in the first paper here, it's shown that if you have depolarizing noise acting in your circuit, then it's very unlikely that the circuit could be used to solve combinatorial optimization problems, because the depolarizing noise, as I said, drives your circuit output state towards the fully entropic or the maximally mixed state. And that state contains no information whatsoever. And on the other hand, we also saw last year that when you have quantum circuits affected by depolarizing noise, then it's actually possible to simulate them in polynomial time, to classically simulate them in polynomial time. And of course, this is kind of bad news for quantum advantage. So a couple of people have come up with the idea of possibly mitigating your noise. And what that means is that you run your quantum algorithm, your near-term quantum algorithm, without doing anything to the noise. So for example, without doing any fault-tolerant procedures. You just run it, and then at the end of it, you correct the errors in post-processing, in classical post-processing. And this is called quantum error mitigation, and I'll talk a bit about this later. But so, in fact, we now come to later. So this is part one of my talk, which is about, the takeaway is that error mitigation is impractical. And this impractical has an asterisk here, which is that it works for the worst case kind of circuit. And I'm going to now explain a little bit. Oh yeah, before that. So this is based on the following paper, exponentially tighter bounds on limitations of quantum error mitigation. And okay, so I'm now going to explain what error mitigation is slightly more formally. So In a world with noiseless quantum computers, what you could do, or how most quantum algorithms work, is that they have a quantum state, and then they put a quantum state into a quantum circuit, running the algorithm of interest, and then they measure the quantum circuit at the end. And what you look at is the expectation value of this measurement. Alternatively, you could also be interested in just drawing samples from the measurement output distribution. But we don't live in an ideal world, and we live in the real world where these quantum circuits are noisy. And this means that you don't get the perfect expectation value or the perfect sample out. What you get is a noisy version. Your expectation value is supposed to be C, it's instead C plus epsilon. And as mentioned earlier, how we model depolarizing noise is that we intersperse the circuit layers with noise. And so what error mitigation is a proposal to kind of put some kind of processing block right after the measurements so that you can hopefully restore the effects, you can reverse the effects of the noise just using this post-processing. And hopefully at the end of this, you get back your almost noiseless expectation values or samples. So here's a concrete example of the protocol that, of the idea that I just sketched out. So here's a protocol that some people have proposed to run on actual devices. So what this protocol is called is zero noise extrapolation, and it's an extrapolation procedure. So that means that you run your circuit of interest at varying noise levels. And what you actually do is you amplify the noise levels. So you run your circuit of interest at these amplified noise levels, and each noise level gives you a corresponding noisy expectation value at that noise level. And then what you do is you put all these expectation values on a plot, and then you extrapolate it back to noise level 0. And this gives you the expectation value at 0 noise. Oh yeah, then you output the extrapolated value, which is the expectation value at 0 noise. Okay, so in the first part of this talk, I considered the possibility of removing quantum noise classically via quantum error mitigation. And I argued that it's actually very impractical in the sense that it consumes a lot of samples. So there are a couple of error mitigation protocols out there. You just saw one called zero noise extrapolation. But here is an excerpt from the IBM research blog on another protocol called probabilistic error cancellation. And it says that the circuit sampling overhead goes kind of exponentially in both the number of qubits and the depth of the circuit. So it was kind of already known previously that for at least this particular protocol, there is an exponential overhead for the number of samples for quantum error mitigation. So this is kind of an early signal that error mitigation is not meant to scale. And also for the protocol that we just saw on zero noise extrapolation, this was another paper, which I cited here, that kind of says that this protocol also suffers from an exponential sampling overhead, but this time the exponential is in the number of qubits n. So I'm going to now attempt to model error mitigation protocols as a whole. And the important parts of this, of error mitigation protocols can be kind of broken down into the following. So you have quantum circuits, you have your noisy quantum circuits, which we model again as having D circuit layers, where every circuit layer is, has like a noisy layer, has a layer of noise after that, and it's on n qubits. So these are two important parameters, the number of qubits and the depth of the circuit. So then the noise model that we consider here is local depolarizing noise. And actually in this paper, we also talk a little bit about non-unital noise. But the model there is a slightly more unrealistic. So let's focus on depolarizing noise for now. So as mentioned, we add like single qubit depolarizing noise after, like a layer of single qubit depolarizing noise after every circuit layer. And then what is the input to the error mitigation algorithm? Well, for every noisy state that is output by such a circuit, we feed in like a bunch of these states to the error mitigation algorithm. And then the goal of the error mitigation algorithm is to output noiseless expectation values or samples. And in our paper, we also differentiate between whether the goal is to output expectation values or samples. But for now, let's focus on just expectation values. So yeah, what is the key point here? You start off with copies of a noisy input state. But what you get out is a function of the noiseless noiseless state. And so then we can pose the question, what is the sample complexity of this denoising protocol? And when I say sample complexity, what I really mean is that I want to understand how many copies of the noisy state does the error mitigation algorithm need in order to estimate these noiseless expectation values to some precision and with some probability, but the precision and the probability are not important parameters. I just want to know what is the answer to this question as a function of the number of qubits of the circuit and the depth of the circuit. Yeah, so the relevant parameters again are the number of qubits of this noiseless circuit and the depth of the noiseless circuit. And again, we assume that the noisy circuit is obtained from the noiseless circuit by putting a layer of noise after every circuit layer. And also, the answer to this question is, of course, going to depend on the strength of the depolarizing noise, which, as defined in the previous slide, was the probability with which the depolarizing noise kind of like replaces your state with the maximally mixed state. So I'm now going to briefly state our theorems. So our theorems are lower bounds. And lower bounds means that we say that you need at least a certain number of copies to do the estimation of the noiseless expectation values. And this number of copies that we give turns out to be exponential in both the number of qubits of the circuit and the depth of the circuit. And this lower bound starts to kick in at basically log n depth. So that's very, very shallow circuits. The second theorem is for a model of non-unital noise. And we see that this exponential in n and d sample complexity also holds for non-unital noise. So how do we interpret our results? Or what do they mean in comparison to previous results? Well, the previous belief was that the number of copies you need is not such a big exponential as what we have here. The previous belief was that you only needed exponential in the depth number of copies. But if we really think about NISQ circuits or near-term circuits, they're going to have very, very short depths. And we don't expect them to have depths greater than log n. But when you raise exponential to the log n, that's only polynomial in n. And so the fact that we can show that exponential in both n and d number of copies is needed means that our result is exponentially stronger because that's a true exponential in n. And this means that certain quantum machine learning subroutines may lose their quantum advantage at much shorter depths than previously thought in the presence of noise. So then you may ask me, why are you talking about noise in a seminar on quantum learning? Well, the answer is because the way we prove this result actually reduces the problem of error mitigation to a problem of statistical inference. And I'm going to now give the framework for how we prove the results, and then we're going to look in detail at one of the steps. So what's the strategy? Our strategy is that for a given error mitigation problem, we define a learning problem such that if you could error mitigate, then that's going to solve the learning problem. And this learning problem, I will describe in more detail later, but it's called noisy state distinguishability. So it's essentially the problem of like distinguishing states, but not just any ordinary quantum states. These are states that are affected by noise. And then what we do is that we get an expression to lower bound the sample complexity of distinguishing such states. And this expression is something that we did not, this is something that has been well known in the statistical inference literature. It comes from Fano's inequality, which for those of you doing information theory is actually the same Fano's inequality that you know. And so what turns out to be the critical quantity here is to study this relative entropy. And what is relative entropy? Relative entropy is like a distance measure between the probability distributions. So for those of you who know about KL divergence, this is like the quantum generalization of that. So this relative entropy here is the distance between your noisy states and the maximally mixed state. And the smaller this quantity is, the harder it is to do error mitigation, which makes total sense because as your noisy states get closer to the maximally mixed states, that gives you an intuition that they become more and more useless or they contain less and less information. So the last step is then, because the output of step number 2 was just an expression, an expression. So the last step of our strategy is just to identify an example of quantum circuits such that this expression becomes enormous, which means that we just construct particular noisy circuits such that this relative entropy is extremely, extremely tiny. So I'm now going to talk in more detail about step 1, which is to show that if you could error mitigate, you could solve this learning problem of distinguishing between noisy states. Okay, so what is the learning problem here? So this problem is called noisy state distinguishability, or that's what I called it at least. And what it is that you are given knowledge of a circuit and some noise channel transforming a circuit to its noisy version. And you're also given m copies of the output state of this circuit. Also, importantly, you know that the original noiseless state was drawn from a known set of states. And then your task is to just output which is the original state. That's called noisy state distinguishability. How many copies m do you need in order to perform this task? So the reason why error mitigation the reason why if you could error mitigate, you could solve noisy state distinguishability comes from the following construction. So imagine you have a noisy state distinguishability problem, which, as mentioned earlier, has the inputs, which are noisy states from a known set. And you are supposed to output what is the index of the state that you were given. What is the index of the noiseless state you were given? Okay, well then I'm going to show you that you can construct a solver for this noisy state distinguishability problem that essentially just does error mitigation. So my boss at Harvard, Boaz Barak, used to call this like a belly protocol. So in the belly of this black box that solves the noisy state distinguishability problem, you can put in an error mitigation problem. And therefore, any lower bound for the noisy state distinguishability problem translates into a lower bound for error mitigation. So what's in the belly of this protocol? Well, it's this error mitigation algorithm here, which takes in these m copies of the noisy output state of the circuit. And then it's just going to estimate these expectation values. Remember, I told you that error mitigation is a protocol that outputs expectation values of the noiseless state given copies of the noisy state. Well, that's exactly what's going on here. And so there are several cases you have to consider, but in fact, there are only 2. So in the case when your original noiseless state was the maximally mixed state, then the expectation value that the algorithm will estimate is going to be 0 for all of the observables here. In the other case, when your noiseless state was drawn from this set of pure states, which are just like the computational basis states, then the error mitigation protocol will output a different set of expectation values. They're going to be different from 0. And because of this, based on the estimates output by error mitigation, you can differentiate whether you were given the maximally mixed state or one of these basis states. And not only that, you know exactly which basis state it was. So this is why you can use error mitigation to solve this particular problem. Yeah, so this is what I just said. Based on the outputs of error mitigation, you can infer the input state to the noisy state distinguishability problem.
Sorry, what was
Yeah.
What were the observables? C.
The observables were just the Z observables.
No, the O sub J.
Oh, I think so. The O's are defined here.
So it's C dot. What is?
It's not C dot. Sorry, that's just like the dot is not supposed to be there. So this is
C
like
of ZJ. So that's like a Heisenberg evolution.
Yeah, you can think of it as like Heisenberg evolution on these ZJs. So C is the noiseless circuit, and yeah, if you just plugged in C of ZJ here, then the C goes to the other side, and then what you get is ZJ rho I.
Should it not be like C inverse? Or is that...
Oh, maybe it's C inverse, but I think it's actually C because when you bring it to the other side, you act with the adjoint.
Okay.
Yeah. Okay. Before I go into part 3, does anyone have more questions on this setup? Yes.
So these are all information theoretic?
Yeah, this is an information theoretic result.
Okay. And then also this distinguishing task, you could just have the set be the zeros state and the mixed state. It could be just 2
yes,
things.
indeed. But you get a weaker bound in that case.
There's no role of having all of them, is that right?
Sorry?
Like, yeah, you could just have 2 in the
Yeah,
set.
if you just have 2, you kind of like can still make this reduction, but you get a weaker bound.
You get a weaker bound?
Yeah. Because like the bound, so Farnell's inequality for multiple hypothesis testing has like some additional factor that you don't get when you're just
And so
testing between two
the set being
hypotheses.
exponentially big gives you an additional. Is it important that the set is like exponentially large, like the set S?
Oh, I think so, but I would have to go back again and look at it.
Okay.
Yeah. Yes?
Yeah, so I have a couple of questions, if that's okay. The first, the example that you gave was for local depolarizing noise, but this seems to hold for anything that has the identity as a fixed point, is that correct?
So you can make the reduction for, oh wait, hang on. What do you mean by this?
So what noise models does this hold to? Is anything that has the identity at the fixed point?
Yeah, there are, so Pauli channels in general all have the identity as the fixed point.
Right. So it works for any of those then?
Yeah, it does. I think this particular proof indeed does that.
Okay. And then my other question, if that's okay, is are you considering error mitigation techniques like virtual distillation, where you can do like entangled measures on the copies of your state?
Oh, I think we do. And at some point in our paper, we talk about how our framework extends to like specific error mitigation techniques. But yeah, I think
right?
Yeah, exactly. You're allowed to do like measurements on all of them, entangling measurements, because here you're measuring separately and then just classically post-processing the data, right? But there you can do like a swap test between those different copies, for instance.
Yeah. In fact, I think we do. The only thing that our model does not allow for is like these intermediate measurements inside the circuit. Changing the operation space on like measuring like part of the circuit, which is what you would do in fault tolerance.
Yeah, so for the lower bound, you prove a couple slides ahead is like, so what's the assumption for the observable and the measurement? Like, if you're calculating some property which only involve local measurement, say first couple of qubits, do you think is still need exponential cost?
Yeah, so we did not consider like how our bound changes for like specific different observables, but I think for like for most, so in particular, if you look at the observables that we have here, if your circuit is very short, this is not going to increase the locality of this single qubit Z by much. So this in particular holds for like a pretty local observable already. Yes.
So just one question to understand correctly. It's critical for your bounds that A doesn't know which circuit is being made, right?
Yes. However, in our, there is this one section in our paper where we differentiate between input state aware and input state agnostic protocols. And I think what you're asking about is protocols that we call input state aware, where the actual knowledge of the circuit is used to construct the error mitigation protocol. And there we show that like, I forget exactly what the result is, but like we show how our proof can be adapted for those methods.
Sorry, but that cannot be without proving the hardness of computing the expectation of the classical, right?
Yeah, I think, okay, so I'm not sure if we actually wrote this, but I believe the hardness of doing error mitigation in that case is like the hardness of like something like classical simulation of the circuit. Yeah. Does anyone have other questions? Yes.
Construct some channel such that this is true. What is the channel?
Sorry, what do you mean by some channel such that this is
Like
true?
what is C?
What is C? Yeah, so that's what I'm going to talk about in the next slide. Any other questions?
So you talked about your lower bound is exponentially small in the number of qubits times the depth. The depth is just measured with respect to all-to-all connectivity of the circuit. There's no geometric location.
Right, exactly. So that's an excellent point. Our worst-case circuits are indeed all-to-all connected. And if you try and make them like geometrically local, then you get an ugly blow-up.
Another question.
Yes.
Just big picture in this error mitigation, am I required to just run the original circuit, which will then get acted upon by noise, by the environment, which is outside my control, or can I run different versions of the original circuit?
Yeah, so I think our proof actually does allow for you to run slightly different versions of the original circuit. But for simplicity, I just presented it as like running the same version. Yes?
OJ, those are N Clifford observables or like any observable?
Oh, so the particular example that we exhibit this for is this this particular circuit, which I will talk about in the next slide, acting on this single qubit Pauli Z's. Yeah. And indeed, the circuit is going to be a Clifford circuit. Any more questions? Okay. So I'm now going to very briefly talk about how we construct these circuits that make this, this quantity basically exponentially small in both n and d. And sigma prime here is the output state of these circuits that we construct. And as hinted at by these cats in the picture, the circuit is a very highly entangling circuit. And part of the reason for that is exactly what I just told Robin, which is that this circuit has all-to-all connectivity, which means that correlations can spread very fast. I guess I may have, sorry. Yeah, I guess that was all I planned to say about like how we constructed these circuits. Sorry, if you want to look at the actual construction of these circuits, you can talk to me later. Okay, sorry for being disappointing. But okay, these circuits are Clifford circuits, and they rely heavily on a construction by Cleve, Leong, and Wang, I think, about how you can basically achieve Clifford 2 designs in extremely short depth. So yeah, and then we show how we can bootstrap this up into like a much larger circuit where kind of like the noise acts kind of at every single circuit layer. But yeah, so the basic construction is you put one of these like Cleve circuits inside here, then you act with noise, then you just show that the circuit scrambles everything very fast, then the noise also scrambles everything very fast. So by the end of this, you get something that's very close to the maximally mixed state. I hope that intuition was at least somewhat useful. Does anyone want more clarification on this?
So you probably need some exponential decay there, right? In this process, by iteration, you need exponential decay to get it like e to the minus. You want this to be exponentially small, right?
Mm-hmm. Right, so without using these special circuits, you can trivially get a bound of e to the minus d. But because we specially constructed these circuits to be
minus d times n or something like this, right?
Oh, maybe there's also an n somewhere, but like e to the, yeah. But because of these circuits, we get e to the minus n times d. Yes?
Do you have any sense of the average case complexity of this problem?
No, because I don't know how to define a distribution over circuit instances. But I really wish I did. If you have any ideas, let me know.
I mean, the Haar measure over circuits, or like drawing two local unitaries randomly is somehow the natural one.
It's hard to capture this, right?
Haar measure over circuits. That's interesting because like what we already use is like some distribution over circuits, but it is not the Haar measure over circuits. Yes?
Where's the D coming in here? So do you look at this particular Clifford circuit at varying depths?
Yeah, so we kind of, okay, so let me go back to the slide where I state the problem. Oh, sorry, I think I may have misunderstood your question, but indeed, yeah, so what you do is like, so our circuits look like this, right? And then if you want to increase the depth, you just like add more of such, you just iterate this more times.
Depth assuming all-to-all connectivity here.
Sorry?
Is depth assuming a particularly all-to-all connectivity structured circuit?
Yeah, this particular circuit has like all-to-all connectivity.
And the D is number of layers of that?
Yes, yes.
Okay.
Yeah. Any more questions? Okay, good. I am now going to go to the second part of this, which is on a totally different noise model. So you may be tempted to conclude from part one that as long as a pre-fault tolerant quantum computing algorithm meets noise, then it might as well go for early retirement. But that is actually not true, strictly, because we can also consider a different type of noise. And that's going to be the content of the second part of this talk, which is non-unital noise. So what is non-unital noise? Well, the mathematical definition is that non-unital noise is noise that doesn't preserve the identity. But what does that actually mean? So let's look at a canonical example, which is amplitude damping noise. So you can think of amplitude damping as a kind of qubit reset. And you can see this by looking at the Krauss operators of amplitude damping noise, which for a particular noise strength are the following two operators. And you see that one of the operators has this off-diagonal entry here, which means that it takes a computational basis state of 1 and projects it back to the computational basis state of 0. So you can think of this as like a kind of noise that, in contrast to depolarizing noise, actually decreases your entropy because it drives you towards the all-zero state. And why do we even model this? Is because it's actually quite close to what you get in physical hardware, or it models certain kinds of processes that you see in physical hardware, like T1 decay and readout error. And there are some cases when you have a mixture of noise, different types of noise in your hardware, and amplitude damping noise is the dominant source of noise. So it's important to also extend our studies of depolarizing noise also to amplitude damping noise and other kinds of non-unital noise. Actually, that's just one reason. Another reason that I didn't even put on the slide is that how does quantum error correction work? What quantum error correction does is it attaches these fresh ancillas in the middle of your circuit. But that is also a kind of noise channel. And that's not going to be unital noise. That's going to be non-unital noise. So non-unital noise is kind of an intermediary regime between the noise that we kind of already know how to study, depolarizing noise, and maybe like a model of more general operations that you can do on your circuit. So what happens when you have both amplitude damping noise and depolarizing noise? So depolarizing noise is a kind of noise that increases the amount of scrambling you have in your distribution. And depolarizing noise actually increases the entropy in your distribution. And because we actually also talked about random quantum circuits, well, that's also something that tries to scramble your distribution. So you can think of depolarizing noise and random circuits as kind of allies. But amplitude damping noise kind of acts in the opposite direction. So it tries to unscramble the distribution by decreasing the amount of entropy in it. And so when you have these two kinds of noise in your circuit, it's interesting to study who wins this fight. Oh, okay. So part 2 is then about non-unital noise. And we show that it actually induces absence of Barren plateaus in quantum machine learning. This is joint work with Antonio, Armando, Shomik, Daniel, and also Jens. So just to give some background before we talk about noise. So a prominent proposal for what you can do with near-term quantum circuits is that it can help with combinatorial optimization. And this proposal goes by the name of variational quantum algorithms. And just to introduce some notation here, you have this quantum circuit which you should think of as consisting only of local gates because that's what we can do in the near term. And let's call each gate Ui. Then the output state of the circuit is going to be a function of what gates you put inside it. And what you do to solve this combinatorial optimization problem is you start off with some Hamiltonian that encodes the combinatorial optimization problem of interest, and then you try and find the UIs that minimize this, this expectation value here. And the answer to this optimization problem then encodes the answer to your optimization problem. Sorry. The answer to this minimization of the energy here encodes the answer to the optimization problem that you started out wanting to solve. So I'm going to call this the cost function. The cost function is some expectation value. And so it's an expectation value of h, which is a Hamiltonian. But Hamiltonians we can think of as being linear combinations of local Pauli observables. So really, when I talk about Barren plateaus, I'm going to be talking about expectation values of local Paulis. So what is Barren plateaus? Barren plateaus is the name given to this phenomenon in such near-term circuits where optimization becomes very expensive because essentially the gradient vanishes in all directions. And when the gradient vanishes, it means that you have no idea which direction you should go in the optimization. So we want to avoid Barren plateaus. But what Barren plateaus can be formalized as is you look at the variance of your cost function with respect to the unitaries in your circuit, to these gates. And you declare that you have a Barren plateau when the variance of this cost function vanishes in the number of qubits. And here an important assumption that I've made is that you randomly choose the gates in your circuit. And I think people make this assumption because that's the situation you are actually in at initialization of this random circuit. So So for this condition to be satisfied means that even at initialization, you don't really know what direction to start moving in at the optimization. So we can ask the question, everything that I said just now was for noiseless circuits, but what if the circuit is actually affected by noise? Well, then it depends on what kind of noise, because it turns out that in the noiseless case, like even when your circuit is not affected by noise, you already start to see that Barren plateaus happen when the depth of your circuit is linear in n. So, and the intuition for this is that at that depth, then if you choose your unitaries ui from a 2 design, then putting them all together in a brickwork architecture converges to a hard random output state. And when you have a hard random output state of the circuit, then that's going to give you exponentially small expectation values. And this happens at linear depth. But you can also think about circuits that are affected by depolarizing noise. And then in that case, also at linear depth, we see Barren plateaus in the circuits. And the cause of these Barren plateaus, in addition to the previous intuition, is that you also have this depolarizing noise, which, as I said just now, drives your output state towards the identity. And what is the identity? It's identity over 2 to the n. So that's why you get this exponential decay in n in the expectation values. And finally, I'm going to advertise our upcoming work a bit. So when you have non-unital noise instead in your circuit, then you actually don't get Barren plateaus. In fact, you can calculate that the variance of the cost function is at least a constant at all depths. And what is the intuition for why there are no Barren plateaus in this case? Well, as I said just now, non-unital noise is a noise that kind of acts counter to depolarizing noise. So it acts like a mini reset operation. So if you imagine that you have non-unital noise kind of interspersed throughout your circuit, then it's going to kind of reset your circuit in a tiny way at every step. And this kind of counteracts the effect of the depolarizing noise in your circuit, as well as the random gates in your circuit, which tends to drive you towards the identity. So then you have a fight between these 2 sources of noise, one increasing entropy and one decreasing entropy, and apparently the one that decreases entropy wins. So that's the end of my talk. So just to summarize the entire presentation in 2 sentences, the first sentence is that error mitigation is hopeless on circuits that scramble information too rapidly. But the second concluding thought is also a direction for future work, which is that non-unital noise is now this type of noise that interestingly decreases entropy, and this flips all our intuitions on their heads. Can we take advantage of this in the intermediate term of quantum computing? And the reason I put a refrigerator here is that there is literally a paper called Quantum Refrigerator, which shows that if you have a quantum circuit affected by non-unital noise, then you can compute for exponential amount of time in the number of qubits. So yeah, I think this is an interesting direction, and I'm happy to talk about this with anyone who wants to. So that's all.